Hi, my name's Valentin Sulzer. I'm a postdoc at Carnegie Mellon University, and today I'll be going over session 4 of the PyBaMM workshop, which is all about experiments. So first we'll start off with some basic experiments, where I'll show how to set up an experiment and how to interact with the solution. And then we will go over to some longer experiments when you want to do hundreds or thousands of cycles. Before we get started, be sure to check out our website pybamm.org if you haven't done so already, and follow us on Twitter at PyBaMM_, and star the repository on GitHub. It really helps us out a lot. So I'm going to get started with the basic experiments. So I've set up my PyBaMM environment, and I've opened up Jupyter Notebook. So now I'm going to import PyBaMM. I'm going to also import some things that are going to be useful later on. So NumPy and Matplotlib. And I'm also going to set the logging level of PyBaMM to notice, which is a level that's useful when you want to track your experiments being solved. So I'll start with probably the most standard experiment in the battery world, which is a CCCV cycle. So in PyBaMM, experiments are set up using the experiment class, and the main thing that needs is a list of steps informing it what to do in the experiment, and you can provide those in very plain English as follows. So first we're going to do a discharge at 1C until we hit the cutoff voltage, which we're going to say is 2.5 volts. Then we're going to rest for an hour, having discharged, and then we're going to do our CV charge, so charge at 1C for until 4.2 volts, and then hold at 4.2 volts until we hit the cutoff voltage, which in this case is going to be C over 50. Okay, so then I'm going to specify which model I'm going to want to solve. In this case, today I'll be working with the single particle model of the electrolyte. My parameter values are going to be the 10, 20, 20 parameter values. Chemistry, so PyBaMM dot parameter sets dot chen 2020, and then I can create my simulation as you saw on day 1 with my model, my experiment, which I've called experiment, and my parameter values, which I've called parameter values. Now, since I've given an experiment, I don't actually need to provide the evaluation time. It's going to calculate that automatically based on the experiment I've given, and with a default period of 60 seconds. So you can change the period by using the period argument in the experiment. And then I'm going to plot the terminal voltage and the current in amps. Now, since I chose the notice logging level, it's going to tell me what it's doing at each step. So in this case, there's only one cycle, and it has 4 steps, and it lists what it's doing and how long it took. And as expected, we get the CC discharge, the rest period, the CC charge, and then the CV hold until we hit the cutoff current. Okay, now let's do something a bit more complicated, which is instead of doing just a single cycle, we're going to do 3 cycles. But actually, it's not that much more complicated, because thanks to Python and list comprehension in Python, we just need to multiply our list by 3, and that just tells it do this thing we're telling it to do, just do it 3 times. So now you can see it's doing 3 cycles, and it's doing 1, 2, 3, and then plotting the result. and we have our 3 CC/CV cycles. So how do we interact with this solution? Well, one way that I just showed is to just do sim.plot or sim.solution.plot equivalently, which plots whichever variables you ask it to plot. Alternatively, I can take a look at sim.solution.cycles, which is a list of solutions corresponding to the different cycles. And say I want to plot the second cycle, so that's index 1 based on 0 indexing. I can plot just the terminal voltage and current of this cycle, and it's only going to plot that cycle, so starting around 4 hours, which is when the second cycle starts, and just that single CC/CV step. I can go even further into the solution and look at each individual step of the cycles. So if I want, for example, only the discharge step of the cycles, now if I look at cycles1.steps, that's another 4 solutions, 1 for each step. And if I do cycles1.steps 0 for just the discharge step, then you see, yeah, this is plotting just the discharge step from a little over 4 volts down to 2.5 volts. Okay, so that's CC/CV. Now, what about if I want to do constant power instead? Well, it's just the same. It's just instead of specifying a number in volts or amps, I have to give a number in watts. So let's check for this parameter set what is the nominal cell capacity, so that we know what power to give, because there's no equivalent of the C rate but for power. So this is a cell with a 5 amp hour capacity, so 1 C would be 5 amps. So let's do this experiment. Let's do PyBaMM.experiment, and let's do a discharge at 5 amps. So this is going to be a constant current discharge at 5 amps until 2.5 volts. Then a charge at, I'm going to put 15 watts, so 5 amps and about an average of 3 volts. That seems like a decent power to charge at. So charge at 15 watts until we hit this 4.2 volt CV hold, and then we're going to do again our CV hold at 4.2 volts until 0.01 amps. And let's just do that once. I'm going to copy my solving code from before, that is unchanged. Except this time I'm also going to plot the terminal power in watts, and you'll see that we have this constant power phase that's replaced the constant current phase. One thing I forgot to mention, which you might be wondering about, is what are these round brackets? The round brackets indicate the cycles. So that's how PyBaMM knows how to group a cycle as opposed to a step. So just to show you, if I were to do remove the round brackets, before it thought it was 1 cycle in 3 steps. If I remove the round brackets, now it thinks that I'm doing 3 separate cycles. Okay. One other thing that you might be interested in is, for example, doing a pulse charge. So this is going to be a little bit more involved, but we can still use the list comprehension from Python to help us set it up. So I'm just going to define my list first before putting it in the experiment. So I'm going to say discharge at 5 amps until 2.5 volts. And then I'm going to do some pulses. So I'm going to charge at 2C for 1 minute. And I'm going to do that with a 1 second period. And then I'm going to rest for 5 minutes. And I'm going to do that with a 10 second period. And I'm going to do 4 pulses, and then I'm going to finish my charge. So I'm going to do charge at 15 watt again for, until 4.2 volts. And I'm going to hold at 4.2 volts until 0.01 amps. Okay, now let me put this PyBaMM experiment equals PyBaMM dot experiment, and I'm gonna give it that tuple, which is the cycle, and as before, I'm gonna set up the simulation, solve and plot. And this time we'll hopefully see some pulses. So we have these 4 pulses. Now let's say we want to zoom into those pulses a bit more, and we don't want to use just the axis limits because we don't want to have to pick exactly where those axis limits are. So again, we're going to access the solution to do this. So one way we could do this, let me just save the solution to this solve object. So the pulses are going to be objects, the steps 1, 2, 3, 4, 5, 6, 7, and 8. So range 1 through to 8, not including 9. The step is going to be the ith step of the 0th cycle. And let me just do PLT, let me just do a simple plot with the time in hours dot data and the terminal voltage, voltage in volts dot data, and let me make all of those red, and let me plot that. Okay. So we have our 8 steps, but it's not a nice continuous plot. It's disjoint because we're plotting each step separately. So what we can do to make a single line is we can construct a solution that consists only of the pulses. So the way I'm going to do that is I'm going to first initialize a pulse solution, which is going to be the first step. And then I'm going to loop through the other step, so now from 2 through to 8, and I'm going to add the step to the pulses. So this plus equals is a little bit of an abusive notation, but it just means take this cycle, this solution object, and stick it on the end of this solution object, and we're doing that in a loop. So we're constructing a long solution object consisting of the 8 steps that make up the pulses. And at the end of that, let's say I want to plot pulses, time in hours.data, and the terminal voltage in volts. So now we have this nice continuous solution. But actually now pulses is just another solution object. If I show you pulses, it's another solution object, which means I can use the plotting functionality from before. And I just use .plot. And that gives me this nice plot with the time labeled and the terminal voltage. And now I could also plot the current, for example. Okay. Last thing I want to show, no, two more things, sorry. So first thing is a GITT example. So this time my cycle is going to be discharge at C/20 for 1 hour, and then rest for 1 hour. So it's pretty similar to the pulsing, and I'm going to do that 20 times, but this is just to show we can do it for a fixed amount of time. And then I'm just going to, now I've defined my cycle, I'm just going to copy this code from before and plot the voltage and the current. So it's going through now, there's 40 steps because I'm doing discharge and hold 20 times. And we have this GITT solution. And now let's say we want to extract the resistance at the end of each GITT step. How would we do that? Well, let's first define a function, which is extract resistance from a step. And the resistance is going to be the step. And PyBaMM has this local ECM resistance variable, which is the terminal voltage minus the open circuit voltage divided by the current. Other way around, open circuit voltage minus terminal voltage divided by the current. So that's what the local resistance would be if we were modeling this using an OCVR model. And I want the end of the step, so I'm going to take the last data point, and then my R's are going to be this function extracting the resistance for the steps in enumerating through all of the steps in the cycle, but only keeping the ones that are even. So if I mod 2 equals 0, and then I'm going to plot the R's. Oops. Oh, I didn't define the solution. Sol is same. It was still using the solution from before. Okay, so now this has length 20, and this shows me the resistance, and it has this kind of quadratic shape that we expect from the resistance because it's dominated by bottle of Vollmer. Okay, the last thing I want to show before we move on to longer experiments is how you can set the initial state of charge for your solution. So my experiment now is just going to be the CCCV step, so no discharges. Let me create it directly. So a single cycle, which is going to be charge at 1C until 4.2 volts, and then hold at 4.2 volts until C over 50. Now I'm going to create an empty list of solutions, initialize that empty list, and I'm going to start from different SOCs, so initial states of charge, 0.6, 0.8. And now I'm going to loop through all of those initial SOCs, and I'm going to create a simulation which uses the same model, same my new experiment. Experiment equals experiment, and the parameter values from before, except now I'm going to solve by setting the initial SOC variable to initial SOC. Going to assign that to Sol, and then I'm going to append that to the solutions. initial typo again. So it's doing them one at a time. And then what I'm going to do is I'm going to plot all of the solutions using PyBaMM.dynamicPlot and compare the different SOCs. And so you can see the red one. So in this current plot, you can see starting from low initial SOC through to higher initial SOC moving in this direction. And say now I want to look at the current during the CV phase. So let me create a subplot. And in the interest of time, I'm just going to copy and paste this code. This is all just standard matplotlib code. And so what I'm doing is I'm taking the first step of the cycle and the second step of the cycle, so the CC step and the CV step. And during the CC step, I'm plotting the voltage, and during the CV step, I'm plotting the current. And so I can see how those change based on my initial SOC, and I can now compare them aligned because I'm initializing at the start of the CV. So I can compare, I can align them more nicely compared to this where they were all staggered because they all started at 0 time. Okay, so that's it for the basic experiments. Next, I'm going to go through some long experiments and show what to do and some tools we can use when we have many more cycles. So I'm going to create a new notebook for that. And as before, I'm going to install the various packages I need, and I'm going to set my logging level to notice, which is going to give me some nice feedback, especially in this case when there's more cycles. For the purpose of this notebook, I'm going to use the parameters from Motart 2020. So params is PyBaMM.parameter values. Chemistry is going to be PyBaMM.parameter sets Motart 2020. And I'm just going to update the SCI kinetics to be pretty fast so that we get some fast degradation and we don't have to wait too long to see the results. So the SCI kinetic rate constant is going to be 10 to the minus 14, which is pretty large for this case. And then I'm going to create a single particle model with an SCI model, which is going to be the EC reaction limited SCI model. If you go to the PyBaMM documentation, you can see all of the SCI models that are available. So if you go to base models, base battery model, and then you scroll down to the SCI options, you can see all of the different SCI models we have implemented and everything else. In this case, I'm going to use the EC reaction limited one. So let me do that. Okay, it's not SCI kinetics race constant. I put an S in kinetics. Okay. Right. Now I'm going to create a new experiment, and it's going to be the usual CC-CV cycling, except I'm going to start with a charge, just because the motard parameters, the initial conditions are fully discharged. So I'm going to do my CC CV first, hold at 4.2 volts until C over 50. Discharge at 1C until, in this case, I'm going to use 3 volts for my lower voltage cutoff, and then rest for 1 hour. And I'm going to do this either 100 times, so 100 cycles, or I'm going to use this termination argument, which tells it if the capacity ever reaches 80% of its initial value, then just stop. So then I'm going to set up my simulation. This should be pretty familiar by now. Model, experiment, and parameter, value just param. And I'm going to do sim.solve. Okay, model is not defined. Right, I called it SPM this time. Params is called params. Okay, and it's going off and it's doing 100 cycles and it's going through telling you which cycle it's currently on. This is a single particle model, so it's fairly quick. And you can see what happened here is by the 50th cycle, the capacity reached 3.947, which is below the stopping capacity of 3.952, which is about 80% of the initial capacity, which was 4.941. So we have our solution. Let's do sim.solution and sol.plot terminal voltage. Okay, and now we have our 100 cycles, but it's not super informative. We just see that them cycling and we can't really see what's going on. There's some other variables though that are a bit more interesting, and I'm gonna just copy and paste them in here. So negative electrode SOC is the average concentration in a negative particle, or the state of charge of that electrode. Positive electrode for the positive electrode. Total lithium in the particles is the weighted sum of the negative and positive electrode SOCs, and then we can see how much lithium has been lost to the negative electrode and the SEI thickness. So now these variables are more interesting because you can see the envelope of the negative electrode SOC changing on positive electrode, and you can see loss of lithium inventory, and you can see some growing SEI thickness. What if I wanted instead to look at each cycle how much lithium is lost and how does that evolve over cycle number? Where what I could do is I can do for I cycle in, again I'm going to use enumerate to get both the index and the number in sim.solution.cycles. For every 10th cycle, so if I is a factor of 10, if I mod 10 is 0, I'm going to do plt.plot. Okay, I'm going to actually, first I'm going to define the cycle. And I want all of the data, and then I'm going to define the loss of lithium inventory to be this variable LLI. Inventory, and that's a percentage. And I want all the data, and I'm going to do plt.plot t shifted by the initial time and LLI shifted by the initial LLI so that everything lines up. And then I can see for every 10th cycle how the loss of lithium inventory is changing. So I haven't labeled these, but in this case I know that it starts with red then blue, so it's decreasing the LLI over each cycle, so it's step limiting. Okay, so that's one way to look at the data from long simulations. We also have something called summary variables, which kind of are variables versus, instead of being against time, they're against cycle number. So if it's a dictionary, so if I plot all of its keys, if I print all of its keys, it's going to tell me all of the summary variables that you can work with. And again, this is just a lot of matplotlib, so I'm just going to copy and paste it. But let's say I want to look at these 6 summary variables. I can do it like this, and this is going to give me a 2x3 plot of all of the summary variables indexed versus cycle number. So just to make that clear, for example, sol.summary variables capacity in amp hours is a numpy array of length 50. So its length is 50 and it's this numpy array. So you can manipulate that and plot it however you want. And what this x0, x100, y0, 100 mean, they're the envelope of the stoichiometries that we saw up here. So they're the min and max values of the stoichiometries. Okay. When you're doing lots of cycles, when it gets to the hundreds and the thousands, and you're saving the entire solution each time, it can get pretty memory intensive, especially if you're doing models like the DFN with very fine discretization. We did the calculation in the past, and you can end up using tens of gigabytes of RAM if you're saving every single cycle. But in actual fact, you probably don't care about every single cycle. You care about some specific cycles, the entire voltage response, and then you care about these summary variables versus cycle number. So we have some tools that allow you to plot, to save only the cycles that you ask it to save. So one thing you can do is tell it to actually only save every 5th cycle, for example. And it's going to solve as usual. Going to go through, it's going to stop at 50. But now if I look at sim.solution.cycles, it's going to save the first cycle. It always saves the first cycle, and then every 5th cycle after that. And the rest of them is just going to put none in there, so that they're spaced out by the right amount. Alternatively, what you can do is give it a list of the values, the cycle numbers you want to save at. So maybe you want to save at the 20th and the 30th and the 45th cycle. I'm going to call this sol list. Again, it's going to solve every single cycle, but it's only going to save some of them. So now if I do sol list dot cycles, give it too many brackets. Okay, if I do sol list dot cycles, it should have none everywhere except in the 1st, 20th, 30th, and 45th cycles. And if you count, you see that is what it does indeed. And now, for example, if I wanted to, I could plot the 45th cycle. Remember, Python uses 0 indexing, so it's going to be the 44th entry of that list. and I can plot the current in amps for that cycle. Sol list, oops, dot cycles. If I try to do instead the 45th cycle, that's not going to work because it's going to tell me none. So if the 45th cycle is just a none, so I can't plot it. Okay. Now, although it's only saved the cycling data for the cycles that I told it to save, it does actually still have the summary variables from every single cycle. So that's much less memory intensive, so it's okay to save all of those. So if I scroll up to my plotting function for summary variables, and then I say sol is sol list. Now it's plotting the summary variables against every single cycle number, even though the actual cycles, the cycling data for that cycle is not saved. And just to show you I'm not cheating, sol list dot summary variables capacity really does have all 50 entries for this case. Okay, one more thing before we go to questions, Q&A, is the starting solution. So one way that you might be exploring PyBaMM is you might have your model and you want to solve it for 100 cycles, look at the solution, and then solve it for another 100 cycles without starting again from scratch, because depending on your model, solving 100 cycles might take some time. So we have an example of how to do that using 10 cycles at a time. I'm just going to copy and paste. It's all stuff you've seen before. I'm doing a CC, CV charge, a discharge and rest, either 10 times or until 80% capacity, and then it's just standard setup, simulation, and solve. Okay. So now it's just doing 10 cycles and it's stopping after 10 cycles, even though the cutoff voltage hasn't been reached yet. But now, say I want to start my next one from where this sol left off. I can do sol2. I'm going to reuse the same simulation object. I'm just going to give it, the starting solution is sol, and now you can see it's starting off from cycle 11. So it left off at 10 and now it's starting from 11. And the capacity is going down from where it left off. And now sol2 has all 20 cycles from before. And if we plot sol2, we'll see that the current and the voltage have those 20 cycles. Okay, so that's it for simulating experiments, and I look forward to your questions on the Q&A.